Welcome students, I am Sudipto Karmakar, Assistant Professor of Physics, Asst. And in today's class we will find the relation between phase velocity and group velocity. Let's start. Now, what is phase velocity? We are going into the mathematical description of phase velocity. Phase velocity or wave velocity which is represented by the notation Vp. P stands for phase, that is equals to omega by k. Now what is omega? Omega is the angular frequency of oscillation. And what is k? K is wave propagation vector or wave propagation constant. And the relation between k and the wavelength lambda or de Broglie wavelength lambda is given by k equals to 2 pi by lambda, where lambda is de Broglie wavelength. That is associated with a moving body. Okay, or in general it is wavelength. Okay, so this is the definition for wave velocity or phase velocity. Now what about group velocity? Group velocity, it is denoted by V suffix G. G stands for group. Okay, so its definition or mathematical definition is differential omega differential k, d omega dk. Okay, so this is our relation or equation number 1 and this is our equation number 2. So from equation number 1 we have Vp equals to omega by k. So from here what we can write? We can write omega equals to Vp into k. Okay, so this is our relation number or equation number 3. Now if we substitute the expression for omega into equation number 2, then we have from equation number 2 and 3 we get, what do we get? On equation number 2 we have group velocity Vg. Okay, so Vg equals to d omega dk. Now in the place of omega I can replace omega by Vp into k. So d dk, that is differentiation with respect to k, that is going to act on Vpk. So we have to differentiate Vpk with respect to k. Okay, so it results taking Vp as constant, it is dk over dk, plus keeping k constant, it is Vp by dVp dk. Okay, so as you can see here, dk it results 1. So as a result we have Vp plus k dVp dk. Okay, so here we are going to apply a chain rule. Vp plus k, I can write dVp dk as dVp d lambda into d lambda dk. Nothing special, I am just applying chain rule. So here we need to evaluate this quantity d lambda dk. Okay, let's evaluate. So as I have already mentioned, k equals to 2 pi by lambda. Okay, so I am writing here k equals to 2 pi by lambda. So from here I can write also lambda equals to 2 pi by k. Now I have to differentiate lambda with respect to k, that results d lambda dk. That is equals to 2 pi is constant and differentiation is going to act on 1 by k. So therefore we have minus of 2 pi by k squared. Okay, so we need to substitute this result here. So therefore on the left hand side we have Vg, that means group velocity. It is equals to, the first term is Vp plus k dVp d lambda into, now the expression for d lambda dk, that is minus of 2 pi by k square, minus of 2 pi by k square. Okay, so as a result we have Vp equals to Vp plus minus minus k dVp d lambda into 2 pi by k square. So this k and this k square cancels out. So we have Vp minus 2 pi by k dVp d lambda. Now, what is 2 pi by k? As you can see, 2 pi by k is nothing but lambda itself. So we have Vp minus lambda dVp d lambda. Okay, so the final result is group velocity, I mean Vg, that is equals to Vp minus lambda dVp over d lambda. So this is our required relation between group velocity and phase velocity. Now, this is a general formulation for group velocity and phase velocity. Now, what if the medium is dispersive or non-dispersive? So let's see. So this is our required relation. Okay. Now let's come to case 1. Here we are considering dispersive medium or normal dispersive medium. Normal dispersive medium. For normal dispersive medium, this phase velocity depends upon the wavelength. That means in normal dispersive medium, phase velocity becomes a function of wavelength. That means a function of lambda. In this kind of medium, phase velocity, that means Vp, is a function of the wavelength lambda. That means this term dVp by d lambda is obviously it is non-zero. So what we can say, if this term is non-zero, and from this above relation between Vg and Vp, we can conclude that since this since this term is non-zero, so there is a quantity which is subtracted from Vp. So so this right hand side represents the group velocity, and since this quantity is subtracted from Vp, so overall result becomes less than Vp. So we can conclude that Vg, that means group velocity, is obviously less than Vp, that means phase velocity. So in case of normal dispersive medium, Vp is a function of lambda, that is the wavelength, and for that reason this quantity becomes non-zero. And since this quantity is non-zero, so there is a certain amount of quantity that is subtracted from Vp. So as a result, Vg becomes less than Vp. So it is true for normal dispersive medium. Okay. Now what about the medium is non-dispersive? So it is case 2. It is very important for exam purpose. Non-dispersive medium. Now, non-dispersive medium are those medium where phase velocity do not depend on lambda. So here phase velocity, that means Vp, is independent of lambda. So that means Vp is constant with respect to lambda. So for that reason, dVp by d lambda, this term goes to 0, because as phase velocity does not depend on lambda, so obviously its differentiation with respect to lambda becomes 0. So what we can tell from this expression? So the expression results Vg, on the right hand side we have Vp minus lambda dVp d lambda. This term goes to 0. So therefore Vp minus lambda into 0, that results Vp. So that means group velocity becomes equal with phase velocity. So in non-dispersive medium, Vg equals to Vp. That means group velocity becomes same as phase velocity. Okay, so this was everything for today's class. I hope it will help you in the examination. Thank you for watching. Done.